All right, my friends, sorry for the delay. Had a bit of trouble getting going on the iPad this morning, but now we're good to go. So, a couple of things about the schedule. If you downloaded the syllabus a long time ago, you should download it again. The Exam 3 is scheduled for March 27th through the 29th. That should also be the date that it's set on the testing center. So that's coming up soon-ish. Another thing is when I planned out the schedule for the semester, I forgot about the spring day that you guys get on March 18th. No? Yes? Friday, 15th, anyway. So there's not going to be class on Friday. Nevertheless, we should be okay to stay on schedule basically as targeted. So let's see. Now I got to turn the display on. It's like I'm a rookie today. There we go. That should do it. So today we are moving on to Chapter 11, which is on oxidation and reduction. And there's something you need to know about oxidation and reduction from an organic chemistry perspective. Though in general chemistry, you probably thought about oxidation as increasing the number of oxygen atoms you have in a molecule. That can sort of be oxidation, but in a more general sense, we're going to see that oxidation is loss of electrons from a molecule. You probably also saw that in general chemistry, but as specifically applied to organic molecules, loss of electrons is going to be accompanied by a decrease in the number of bonds between carbon and hydrogen. So I'm not actually going to specify sigma or pi. I'm just going to say a decrease in the number of carbon-hydrogen bonds, or it can be an increase in the number of carbon heteroatom bonds where Z is an electronegative heteroatom like nitrogen, oxygen, halides, etc. Okay? So you've seen an example of an oxidation reaction very recently. Alkene halogenation is an oxidation reaction, though we didn't tell you it was. This is an increase in the number of carbon heteroatom bonds. All right, but you'll see other examples of oxidation this semester. So we're going to learn how to take an alkene and turn it into an epoxide. We actually have a way to do that we learned in Chapter 10. It involved forming a halohydrin sort of under these bromination conditions, but we'll learn about that. We're also going to learn how to take an alcohol and convert it into an aldehyde, and to take an aldehyde and convert it into a carboxylic acid. And you can see that in each of those cases, I am getting rid of a carbon-hydrogen bond and replacing it with a carbon-oxygen bond. So you can follow oxidation by loss of carbon-hydrogen bonds or by increase in the number of carbon heteroatom bonds. Do you see that the aldehyde has one more carbon-oxygen bond than the alcohol, and the carboxylic acid has one more carbon-oxygen bond than the aldehyde? Similarly, in this chapter, we'll see a secondary alcohol with the mystery reagent. Are you excited to learn what that is? Converts to a ketone. So we'll learn all kinds of different reagents in this chapter, but they're going to be united under this theme of oxidation, or reagents that decrease the number of electrons in a molecule, or decrease the number of carbon-hydrogen bonds, or increase the number of carbon heteroatom bonds. Reduction we can define as just the opposite of oxidation. By the way, you can't ever just do one. In an oxidation-reduction reaction, one molecule gets oxidized, the other gets reduced. Where do the electrons go when something is oxidized? Well, they go to the reagent that's doing, they go to something that gets reduced. So reduction is a gain of electrons, and this is going to lead to an increase in the number of carbon-hydrogen bonds, a decrease in the number of carbon heteroatom bonds, and some examples of reduction. I'm not sure we've actually seen any of these yet. We're going to do a few new reduction reactions. We'll take an alkene, and with a mystery reagent, we'll convert it into the alkane. So you can see there that we're increasing the number of carbon-hydrogen bonds. It may be worth your time occasionally as considering reduction reactions to fill in the hydrogens that are usually not shown but are implied. This is C2H4, this is C2H6. You can see that we're basically adding hydrogen. This reaction is called a hydrogenation reaction, and it involves a gain of carbon-hydrogen bonds. We'll see we can do the same for the alkyne. So we're going to have reduction conditions that convert this same alkyne into this C2H6 starting material, product. We'll also see that we're going to have two different sets of reduction conditions that can convert the alkyne into the cis-alkene. And we'll also have a complementary set of reduction conditions that can convert into the trans-alkene. So stay tuned for that. Both of those are reduction reactions. Both of them basically involve adding hydrogen across H2 across a pi bond. Each carbon of the pi bond gets a hydrogen. So that's reduction. We'll do one other reduction reaction in this chapter 11. It will be to take something like an epoxide, and we're going to use a reagent to convert the epoxide into the corresponding alcohol. And if you look at what's changed here, again, we've got an increase in the number of carbon-hydrogen bonds. And maybe I'll just highlight those in all of these examples. Finally, not in 351, but later in 352, you're going to learn reaction conditions that will take aldehydes and turn them into alcohols. You'll learn reduction conditions that take ketones and turn them into alcohols. And there'll be some other examples. You'll learn about converting things that are roughly at the same oxidation state as a carboxylic acid, for example, an ester. We'll learn how to reduce esters to aldehydes and or to alcohols. Okay, but again, all of sort of the stuff here is a 352 reaction. They could put it in this section of the text, and that would be fine, but I think your Professor Smith, the text author, wants you to know some things about carbonyl containing molecules and their chemistry before worrying about these reactions. All right, so with that introduction, let's dive in. We're going to do reduction first. I will point out as we go mechanistic details you need to know versus those you don't need to know. You'll need to make notes to yourself to keep track of that. So here we are. The first set of reactions, reduction reactions, are called hydrogenation reactions. And these are reactions that basically add hydrogen across a pi bond. So let's take an alkene, and I'm deliberately choosing this alkene to illustrate some stereochemical issues of this reaction. The reagents for this reaction are actually just hydrogen gas, H2, and then we need a catalyst, and the catalyst is palladium metal, though the efficiency of the catalyst depends on its surface area. You want as much palladium metal exposed to the alkene and to hydrogen as possible. And because of this, they grind up the palladium metal into powder and mix it with carbon and basically immobilize the palladium on carbon. That preparation of palladium on carbon is PD/C. Any organic chemist knows what you're talking about when you say that. The mechanism of the reaction is beyond the scope of the class. I'll give you a little bit of insight into what's going on. What you see, however, is the syn addition of hydrogen across the pi bond. So if you imagine the surface of palladium metal immobilized on charcoal, you have a series of palladium atoms close to each other. And what the arrow pushing for this reaction is not really important for this class, but there's more to be understood here, but it's sort of beyond the scope. Palladium breaks the hydrogen apart into two pieces, and you have two adjacent palladium metals, both of which are bonded to hydrogen. So before hydrogen bonds to the metal, it's like this. After hydrogen bonds to the metal, it looks like this. These two electrons from the hydrogen bond are in one of these hydrogen palladium bonds. The electrons in the other bond actually come from the palladium metal. That detail is not significant, but it may help you to follow along what's happening. The alkene sits down on the surface of the palladium metal. So I'm drawing this alkene as though it were sort of lowering down onto the surface of the palladium metal. And both hydrogens get added to the same face of that alkene. You can show that mechanism happening in this way. The pi bond attacks the one hydrogen, and those electrons go back onto palladium, and then these electrons from the hydrogen come up and attack. That arrow pushing, again, is only to help you know what happens. I'm never going to ask you to reproduce that. But the point is that both hydrogens get added to the same side of the alkene, and you go from alkene to alkane, and that's a reduction. Right? Questions so far? Yeah.
Would we get the enantiomer of the alkene as well?
If it were chiral, would you get the enantiomer? Yes, because the top face and the bottom face of the alkane or alkene are identical. In this case, that's a meso compound. Yeah. So it's not chiral, so you don't have to worry about that. A few practical issues. Hydrogen's a gas, so it's not like you can weigh it out on a stir plate or weigh it out on a mass balance and then pour it into your reaction vessel. The way people do this in the lab, there's many different techniques for this, but one of the most common is to just fill a balloon with hydrogen, and then you tape the balloon to a syringe, a plastic syringe. You put a needle on the end of that plastic syringe, so you have to be careful not to pop your balloon or to poke yourself. And then you push that needle through a rubber septum that's on top of a round bottom flask. and then the hydrogen that is inside that balloon is then exposed to what's in the flask, and that's enough to do the reaction. So you have in solution your alkene of whatever it is, and then at the bottom you also have your palladium on carbon catalyst. You stir it, and that's usually enough to get the reaction to go. If you do this with a balloon, the pressure of the hydrogen is 1 atmosphere because you got 1 atmosphere pushing on the balloon. Some reactions you need to pressurize the hydrogen even more, and there are special reaction vessels that allow you to do that. You have been exposed to this kind of hydrogenation chemistry for your entire life, ever since you've been eating products that have partially hydrogenated vegetable oils in them, because this is how they do that. They use a catalyst, they use hydrogen. We talked about this in the chapter on non-covalent interactions, chapter 3, where we talked about how vegetable oils have cis double bonds in them, that those are, now you know from chapter 10 that double bonds are reactive, can do lots of interesting chemistry. To prevent the reactivity of the double bond, which sometimes gets oxidized in vegetable oil, resulting in rancidity. You remember the horrible cautionary tale of the rancid tostada shells of 2016? Remember that? Yeah. So to avoid that, food companies will hydrogenate the oil, reducing the double bond now to just an alkane. That changes the properties of the oil. It generally makes things become more solid because the non-covalent interactions are stronger, but it also prevents oxidation. To some extent, this reduction reaction is a little bit reversible. If you don't push it to completeness, you can get isomerization of the double bond from cis to trans, and that's sort of the origin of trans fats and oils that we talked about. Okay, so that's alkene reduction. Question, let's see, 27 on your exam asked you to calculate the thermodynamics, is it endothermic or exothermic, for an alkene hydrogenation reaction. You saw the starting materials and the products, you didn't know how it happened, this is now how it happened. So let's talk about alkynes. You can use the same hydrogen and palladium catalyst to take an alkyne and reduce it all the way to the alkane without stopping at the alkene. So if I just use my regular hydrogen and palladium on carbon catalyst, that will take the 2 carbons of my alkyne and it will give each of them 2 carbon hydrogen bonds. In this, the reaction will give me will add 2 equivalents of hydrogen across the double bond. So in pink is the first equivalent and in blue is the second equivalent. There's an intermediate along the way, which would be the cis alkene, but you can't stop at the cis alkene when you use the palladium catalyst. That should make sense because we've already used these same conditions to reduce alkenes to alkanes. So the first equivalent of hydrogen goes on and then the reaction continues onward. The second equivalent of hydrogen goes on and you end up with your alkane. All right? So to some extent, students always ask, how do I manage all these reactions? What do I need to memorize and what do I not need to memorize? And the answer is there's a lot of different styles, but in cases where we don't talk in a lot of detail about the mechanism, there are a lot of details you're going to have to memorize. For example, the detail that the alkane can be reduced to the alkyne can be reduced to the alkane might not be something you have to memorize, but you might have to memorize that the alkyne doesn't stop at the alkene intermediate. All right, questions so far? Yeah. Always syn addition, yes. And the reason for that is governed by the fact that the alkene has to sit down on the olefin surface, and all the hydrogens are added from, the metal surface, and all the hydrogens are added from that metal surface to the same side of the alkene. Others? Okay. What if you wanted to stop at the alkane? I'm going to get that wrong. Good golly. Okay. Alkyne, alkene, and alkane. An alternative word for alkene, since I'm struggling with it, it sort of comes from the oil industry, is olefin. It sounds like Sam Gamgee's Oliphants from Lord of the Rings. Those references are never as popular as my Star Wars references, but we'll try. Anyway, olefin, you'll hear me talk about olefins, and those are, you can use that term interchangeably with alkene. It's a little less nasally when I say it, so maybe I'll try it. All right, what if you wanted to stop at the olefin from the alkyne? We do have conditions for that, and there are two of them. I alluded to those at the beginning of class. I said we were going to have a way to turn the alkyne into the cis olefin and to the trans olefin. So let's do cis first. It turns out that people discovered not too long after the discovery of the hydrogenation reaction that if you wanted to stop at the olefin, strategy one is to use a poisoned version of the palladium on carbon catalyst. By poisoned, we mean we're going to add something to the catalyst to decrease its reactivity, to make it so it's reactive enough to make the alkyne go to the olefin, but not reactive enough to make the olefin go all the way to the alkane. So your text may talk a little bit about this. We aren't going to talk about it in any detail. It's something they add to the palladium. There's a proprietary, though actually its composition is known, catalyst called the Lindlar catalyst, which is this poisoned version of the palladium on carbon catalyst. And again, this is going to be something you have to memorize because we're not explaining how or why it happens. But it has all of the features of the palladium on carbon catalyst. The reduction still happens at a metal surface. You still get syn addition of hydrogen, only you stop after the addition of the first equivalent, so you're able to stop at the olefin. So if you use the Lindlar catalyst, you can take the alkyne starting material and the product will be the cis alkene or the cis olefin. Here's that first equivalent of hydrogen that we added, and we don't add a second equivalent. So that's a fun strategy, and actually that illustrates a really important principle in organic chemistry, and chemistry in general is if you can take the same starting materials but just tweak the catalyst and get a different product, that's highly useful. Catalysts can be reused. You only need to fix one thing as opposed to redesigning the entire reaction. So this is an example of that. We've tweaked the catalyst, we added some things to the palladium that made it a little bit less reactive, and now we're able to stop at the alkene, or stop at the olefin. Dang, I'm gonna get that wrong. Do you see how it's still a syn addition? The two hydrogens got added to the same side of the double bond? Okay. All right, what if you wanted the trans product where the hydrogens were added to opposite sides? So far, all we've done for reduction is involved a metal surface where both hydrogens are on this metal surface and they get added to the same side of the molecule that you're reacting. So we're going to need a different strategy for reduction to give the trans alkene or the trans olefin. So strategy number 2 is called the dissolving metal reduction. It also involves a metal. The mechanism for this reaction is known. It is shown in your text. However, in my opinion, the juice is not worth the squeeze. So if you want to look at that mechanism and understand it, it will help you remember that this reaction gives you the trans product. So I certainly don't discourage you from looking at it. However, we're not going to take class time to talk about it, nor am I going to ask you about the mechanism. So what is dissolving metal reduction? It turns out that you can take sodium metal in its zero oxidation state. So that's Na0. The 0 is just to remind you that it's in its zero oxidation state. It's not sodium plus. And if you put it in liquid ammonia, okay, so NH3 is a gas. When you go to the store and buy ammonia, what you're really buying is NH3 dissolved in water, whereupon it becomes like ammonium hydroxide. But NH3 itself is a gas. You can cool it and condense it to a liquid. And then if you have liquid ammonia, the sodium will actually dissolve in the liquid ammonia. So if you add sodium and liquid ammonia, what you end up getting is sodium plus and an electron. Sodium ejects an electron. This is really weird, and this is why we're not worrying about that. That electron actually exists within a cage of ammonia molecules. You can think of it as if the individual ammonia molecules were hydrogen bonding with the electron. It's kind of bizarre. If you want to know what the color of a dissolved electron, an electron that's solvated by ammonia ions is, it's dark blue. It's kind of crazy. Never knew what a dissolved electron would look like before. So we'll color that. Let's see, if we got a dark blue color, maybe we do. Ooh, that's nice. And that dissolved electron is what does the reduction. Actually, it gets added to the pi star of the alkyne to create an anion, and then that alkyne picks up a proton, that anionic alkyne picks up a proton from ammonia, and that happens in a stepwise fashion. In any case, as I said, if you want to know more, there are details in your text and a known mechanism that could help. But rather than spend more time on it, I think you can get what you need to from this reaction simply by memorization. So the reagent is sodium metal and ammonia, and that will deliver one equivalent of hydrogen to the alkyne. It happens in a stepwise fashion, and you get the more stable alkyne product where those hydrogens are there, okay? So this gives you exclusively the trans olefin. All right. So now we have two complementary ways to get different olefin stereochemistry. People mix this reagent up all the time. With NaNH2. And that's not the dissolving metal reduction. That's just a really strong base that we've used before when converting 1,2 dibromides into alkynes. So there's a potential source of confusion here. You're going to have to find a way to remember. I'm warning you now. People do it all the time, so I'm just warning you in advance. You're going to have to find a way of separating in your mind the dissolving metal reduction from the use of NaNH2 as a base. I just want to take a moment and illustrate the kinds of things you can do with stereochemistry. Stereochemistry and synthesis with these reactions. So suppose I say your starting material has to be this alkyne, and suppose I give you the option of two different products. I want this product A, well, sure, fine, and then it's diastereomer B. Ooh, stereochemistry again. Dun, dun, dun. Which of these is chiral? A, B, or both? Oh, you think A is chiral, do you? You want to reconsider that? Yes, you would like to reconsider that? Yes. A is a concealed meso compound. I got you again. Don't let that happen again, okay? A is a concealed meso compound, is not chiral. B is chiral. We'll put a plus minus to indicate that I can get both enantiomers there. Now, how do I get A or B from this same starting material? You're going to have to think backwards a little bit. First, notice that the product is, both products are 1,2-dibromides or vicinal dibromides. We know what reaction gives us a dibromide. It's alkene halogenation. The key question is, can you tell from the 1,2-dibromide what the stereochemistry of the alkene had to be? Remember, halogenation is an anti-addition. The bromos get added to opposite sides of the original alkene. So for A, it would make sense that the original alkene was this trans alkene. Can you see that? If you can't, you are going to lose 8 points on the exam at least. So go fix that. That's going to take practice. And I can tell you it, but it's not going to stick if you don't practice it. Now, how about the one below? This is tricky. The two bromos are shown on the same side. I did that on purpose because I am evil. In the Dr. Doofenshmirtz sense, not necessarily in the really, really evil sense. But I don't know, you may have opinions. Actually, in filtering through the exams, I saw, I don't know who it was, but I saw one of you wrote on the front page of the exam, "I'm ready, Joshua, bring it." I felt kind of good about that, like I'm the evil nemesis, sort of. I encourage you, like Perry the Platypus, to thwart me, okay? I spent all this time monologuing and disclosing my evil secrets and my innators, so please prepare to thwart me. Here's how you thwart me on this problem. I've drawn the molecule deliberately so as the bromos are on the same on the same side of this molecule. You have to realize that halogenation is an anti-addition process, and if you want to see that and to see what the alkene starting material would be, you can rotate around this carbon-carbon bond into a configuration where you see clearly that one bromo is up and the other is down. That would tell you that the precursor to that 1,2-dibromide is the cis olefin. Again, if you can't see that, you need to fix that. Building a model would help. So if the trans olefin is the starting material, or the intermediate rather, for product A, what conditions do I use to get the trans olefin from this alkyne? That's the dissolving metal reduction, sodium and ammonia. In contrast, if I want the cis alkene from the alkyne, that's the hydrogen and Lindlar catalyst. Okay? I mean, that's a lot of stereochemical issues. I love to throw that one on the exam. That's probably going to show up in more than one question. Okay, so you have been warned. All right, let's do the final reduction reaction. And that is going to be what I mentioned at the beginning of the class, which is reduction of an epoxide. Notice our starting material is going to be an epoxide. Our product is going to be an alcohol. And we will have added a hydrogen to the epoxide as a nucleophile. So if that's our goal, epoxide reduction, you might wonder if I want to take this epoxide and I want a reagent that will add a hydrogen to the epoxide as a nucleophile, why don't I just use sodium hydride? Why can't I just have H minus go like this? That would give me an intermediate that looked like this with a negatively charged oxygen. And then when I do aqueous workup and add water, I can neutralize that negatively charged oxygen like this to get my alcohol product. The reason is that hydride H minus on its own is not a good nucleophile, mostly because NaH, sodium hydride, you can't buy H minus on its own, it has to have a counter ion, is very insoluble in organic solvent. You can use it as a base, but not as a nucleophile, because each individual hydride can't actually float off into solution and attack carbons. So we need a hydride delivery reagent. The DoorDash of the hydride world, bringing it directly to where it needs to be. And there are a few of these. Nature has some that we'll talk about, and then chemistry, which I guess is part of nature, has some. So BH4, let's see, yep. Negative formal charge on the boron. Sodium is generally the counter ion. You will see this written as sodium borohydride. And then there's a related reagent, this sort of close cousin of sodium borohydride is lithium aluminum hydride. For some reason, lithium is the counter ion of choice with the aluminum hydride reagent. These are hydride delivery reagents. The negative formal charge is on the boron or on the aluminum. You can see that it should have a negative formal charge because aluminum and boron normally come with 3 valence electrons. Here they own 4, they're bonded to 4 things, so you got a negative formal charge. Boron and aluminum are actually less electronegative than hydrogen. So because hydrogen is more electronegative than boron or aluminum, there's actually a huge amount of delta minus on the hydrogen. And because both boron and aluminum are comfortable being neutral and having an empty p orbital, it's actually really easy for these reagents to deliver a hydride to some source and simply hand off the H minus. H minus leaves from boron and gets handed directly to whatever it's attacking. I'll point out real briefly that nature has a few hydride delivery reagents. One of these is called NADH, which stands for, you're not going to want to know this, nicotinamide adenine dinucleotide. I will show you only part of this molecule. Already too much, right? This is just the nicotinamide portion. This R group here is the adenine dinucleotide portion, and you don't want to see it right now. I don't want to draw it. You don't necessarily want to see it. Look it up. But in each of these cases, this is the hydride that gets delivered from aluminum hydride. This is the hydride that gets delivered from borohydride. One of these two hydrogens, and it depends on the reaction, is the one that gets delivered for nicotinamide adenine dinucleotide. I could show you, it may be helpful for you to see sort of the form after the reduction reaction. So BH3, ALH3 without the hydride, and then for NADH, it's NAD plus. I'll show you what that looks like. You can see that in each case, loss of the hydride from the borohydride reagent is an oxidation, right? We lose a bond between an atom and hydrogen. Or in this case with NADH, we lose a carbon-hydrogen bond. These hydride delivery reagents are reducing reagents. They reduce their reactive partner. They themselves, in so doing, get oxidized. So for our epoxide opening reaction, let me show you with lithium aluminum hydride how this would work. Suppose your epoxide is this one, where carbon A and B of the epoxide are not the same. If you use lithium aluminum hydride as the reagent, we're going to treat this like a strong nucleophile. It's going to open up an epoxide under SN2 conditions. And because we're opening the epoxide under strong nucleophile conditions, not acidic conditions, the nucleophile will attack at the less substituted carbon, like we learned in Chapter 10, and that's because of sterics. To show this mechanism, you'll simply draw out the aluminum hydride reagent with a negative formal charge on the aluminum. You will push an arrow from the aluminum hydrogen bond. Hydride leaves with its electrons and attacks. It's a direct handoff. Hydride is never floating out on its own. It's directly handed off from the aluminum hydride to carbon B of the epoxide, and we break the carbon-oxygen bond. SN2 style, we're attacking the carbon-oxygen sigma star with the hydride reagent. The intermediate looks like this. It's all the same stereochemical issues apply. Here in the example I've chosen, there really aren't any to worry about because the carbon B that we attack is not a stereocenter. Nevertheless, because it opens up from the backside under a sort of SN2 mechanism, we expect inversion of configuration if the attack is happening at a stereocenter. And so you would get this product, and then again, after aqueous workup, you would protonate the negatively charged oxygen to get this alcohol product. I'm going to rely on you to be able to follow through all of the relevant stereochemical issues for this reaction, backside attack, inversion of configuration. The example I chose illustrates the regiochemical issues, which is we attack the less substituted carbon, but it doesn't demonstrate any stereochemical issues because we're not making a stereocenter. Okay, so we'll come back in 352 to lithium aluminum hydride and sodium borohydride as reducing reagents. For now, the one reaction you're learning is epoxide opening, but be prepared in 352 for some stuff with ketones and aldehydes and esters and so on. All right, that's the reduction reactions. We're going to now go to oxidation reactions. Before we do, questions? Yes?
Does the boron hydride, does that follow the same as the reaction?
The sodium borohydride would follow the same basic mechanism. You will learn in 352 that sodium borohydride is not as reactive as lithium aluminum hydride because aluminum is way less electronegative, because the electronegativity difference between aluminum and hydrogen is larger than between boron and hydrogen. Nevertheless, that distinction is not really important for now. Okay, so let's talk oxidation. And our first oxidation reaction is going to be going from an olefin to an epoxide. So we've done an example of this before. Here is an alkene. Here are the conditions for halohydrin formation. Notice that halohydrin formation is an oxidation reaction because we're increasing the number of carbon heteroatom bonds. Then I believe we mentioned before that if you use sodium hydride as a base, you can remove the proton from the oxygen. That creates a nucleophile in the same molecule as you have a leaving group, and then that leaving group can snap, then the nucleophile can attack the leaving group, the ring snaps shut, and we make an epoxide. So that's a two-step reaction sequence. However, there are reagents that can do the same reaction in one step. And a big area of organic chemistry is about doing reactions more efficiently and cheaply. If you have a reaction that you can do in one step instead of two, that often saves you a lot of time and money. So we're going to introduce a new reagent that takes the olefin and goes directly to the epoxide without the need of an intermediate. This reagent has a name that's complicated, and so we will often refer to it by an acronym, and that's humans and their acronyms. It's kind of annoying, it's alphabet soup, but you'll see why we use the acronym when I write down the name of this reagent. Meta-chloro-peroxy benzoic acid. And now we need a NAP, MCPBA. I'll draw the reagent for you. There's the metachloro, here's the benzoic acid part, and here's the peroxy part. So that's what the reagent looks like. And the business end of the molecule is this oxygen-oxygen bond. Oxygen-oxygen bonds are relatively weak. You can look up their bond dissociation energies. They break pretty easily. And so you will find that this is an oxidizing agent. You will find that a lot of oxidizing agents have bonds between oxygen and oxygen, or perhaps bonds between nitrogen and oxygen. The weakness of that bond makes it so that you can do the reactions that we'll talk about. All right, that's enough for today. So now we are on OChem weekend. We'll see you Monday.